The premise behind my talk today was there's an area that I look into at KPMG, which is I call energy efficient application architectures. I know that sounds like a bit of a mouthful, but what I'm looking at is how to build applications in a way that you're optimizing not just for compute usage, not just for memory usage, but also for energy usage. That creates a whole bunch of challenges. It creates some interesting thinking around how that's done. And what I'm going to do today is actually take you on that journey of the work that I've done over the last 6 months or so as I've been building this out. But I'm going to have to go back to the start and actually talk about data centers. Oh, I need to make sure I don't walk off. Right, so when we talk about data centers, we talk about the key sort of principles behind how they're built. And I'm sure there's nothing on the screen right now which is a surprise to you. These data centers, when we build them, they need to be performant, they need to be reliable, they need to be scalable, they need to be very efficient with how they use their energy, they need to be secure, and they need to be easy to maintain. When we talk about performance, we're not just talking about compute, we're talking about network, we're talking about storage. When we talk about reliability, we're talking about multiple layers of reliability, so at the compute layer, at the network layer, at the energy layer. When we talk about scalability, it's the same thing. Compute needs to be able to scale, but then so does energy. If we need to get a bigger pipe into the data center because the energy demands are growing, it has to scale. But also we need to look at energy efficiency. So metrics around power usage efficiency get thrown around quite a lot when we're talking about data centers. The percentage of energy, renewable energy that's being used by a location, for example. These are the type of metrics we look at. When we talk about security, we're not just talking about cyber security, we're talking about physical security of the location as well. And finally, maintainability. We need to be able to run the data center, otherwise we're going to end up in a whole lot of trouble. Now, what that goes to, when we take this down into the components, some of the things I just mentioned. So we've obviously got the compute infrastructure, where we talk about things like the HPC clusters themselves, which are running the workloads, the network layer, the storage layer. But then we have to think of some of the peripheral systems as well. So, for example, cooling, whether that's air-based cooling or whether that's liquid cooling, so immersion systems, for example. Then we go into the power layer. We start talking about things like uninterruptible power supplies, on-site generators, and then how do you manage that? How do you monitor all of that? As we go back to the compute layer and we start looking at the clusters themselves, how do you actually monitor the availability of your devices, make sure they're all online? And then finally, as I mentioned earlier, security is not just about physical security, but it's about the cyber security of the workloads that you're running as well. So if we take that through to the design considerations and what we're actually doing when we build the data centers, we need to make sure they're modular, because we obviously know that the workload and the demands of today are not necessarily the workloads and the demands of tomorrow. What's happened with AI-based workloads over the last year or so, that's clear evidence of that, and there's obviously a massive demand now to increase these sites. And unless you've built your data center in a very modular way, you're not going to be able to do that. Again, scalability for future demand, making sure that you're being very energy efficient. Sustainability, that's obviously a key talking point for today. Considering the environmental impact, the energy consumption, how you reduce that word which Matt doesn't like talking about, which is waste. And this is something I'm going to touch on a bit later, and how we think about, where we think about the products that data centers produce, what we would think of as waste and what we think of as products. Finally, it should be flexible as well as workloads and technologies change. Now, one of the things I want to talk about is the types of loads that go inside data centers. So there's two types of loading when we talk about energy usage. There's firm loading and flexible loading. And when we talk about firm loading, what we're actually talking about is something that has a consistent demand for electricity. This is usually something that a data center provider would purchase in advance via a power purchase agreement, for example. It's continued wattage, it's very, very predictable, very stable. Then there's the flexible load, where you have massive variability in terms of how the energy is actually being consumed. It's variable, it's less guaranteed. Now, why is this relevant, you're probably wondering? Well, I'll come on to that in a second, but if we're talking about firm loads themselves and we want to actually orchestrate what's going on inside the data center to be careful about how we use energy, we have to be very careful. Firm loads by their nature are things that cannot be interrupted. Now, if you want to go down the realm of where you're building applications in a way where you can take devices offline if needed, you need to be very careful with, first of all, how you identify workloads that can be taken down and workloads that can't be taken down. For example, many of you will be familiar with taking down pre-production environments when there's constraints on compute environments. It's something that many people will do. Many people use automation to take down dev and test environments outside of office hours, for example. Why do you need dev and test to be online over the weekend, for example? But if you're now going to do this where you're doing this for non-dev and test workloads, you need to be very, very careful. There's technical challenges this introduces, because now you need to think about how resources are being allocated, how you're potentially using virtualization or cloud environments. There's organizational challenges, because if you're now orchestrating these types of offline events where you're bringing things up and down, you need to make sure there's clear communication, clear reporting, and how this is being done inside your environment. You also need to be mindful of the business impact. For example, if you're orchestrating the bringing up and down of workloads, we need to make sure that it doesn't happen in a way that affects the revenue of the business or affects any of the customer satisfaction. For example, if a bank were to suddenly take down the back end running its mobile app over a weekend, a lot of people are going to be really irritated. Obviously, the regulators will be quite interested in that as well, and that's going to lead to a lot of reputational damage. There's also ethical considerations. How do you do this in a fair and transparent way if you're suddenly orchestrating workloads? Now, when we take that thinking forward to AI models, what we get into is we start to look at the modes in which models run. And there's two modes in which models run. We talk about inference mode and training mode. Anyone that's used ChatGPT, I'm pretty sure everyone in this room has, when you communicate with ChatGPT, what you're actually doing is using a model that's already been trained and actually using it in inference mode. You're sending it requests, it is processing that request, and it is sending information back to you. When something's running in, when something's in training mode, it's actually just training. It's the model's learning. Now, the way these two models actually consume energy and the way they consume compute is very different. Training has a very high baseline, but a very consistent consumption, whereas inference by its nature is very spiky. Now, what this means is when you're talking about the potentially of taking workloads down or curtailing the amount of compute they have, you can't do that with training mode, models that are running in training mode, because they need to be able to run through. Inference mode is where it gets quite interesting, is because if you have compute demands which are fluctuating quite heavily, do you need to have all that compute capacity when it's not needed? And this is where you go into the question of, okay, well, if you're now running predominantly all of your models in inference mode, can you actually bring them down at a time when they're not being used? So, again, now if we jump forward to, again, mentioning ChatGPT, a lot of people will use inference as a service. So they won't actually train the models themselves. They will run pre-trained models and they will just run requests through to them. What this means is you don't actually have to provide all of the energy required to train the model, you just consume it once it's been trained. ChatGPT being the most obvious example of that. Where you can also be quite efficient with how you use energy is you can actually use energy efficient coding methods. So there's a lot of benchmarking that's been done around application programming languages and which ones are the most energy efficient. So for example, if you look at Python, and which is the language that's used quite commonly, it's estimated that consumes, because of the way it consumes compute capacity, it's estimated that it's almost 75 times more energy consumption when running something like Python versus running C, for example. C is a very efficient language, but there's obviously some serious considerations as to why you might not necessarily use C as a modern language for building applications. Where this gets quite interesting is you can use something like Rust, for example. Rust is commonly considered to be the modern version of C++, very energy efficient, very safe to use. You can optimize your algorithms around how you actually do your coding. So for example, refactoring your code, making sure you're very efficient with how you do things. Again, this leads into memory usage, making sure you do things in parallel, so you're running multiple threads and making best use of your architecture. Removing redundant code. You'll be surprised how much code just gets left in applications which isn't actually doing anything, is just contributing to bloat and contributing to the size of the application. Data types as well. For example, if we use something like just number-based variables, why would you use massive variables when you can use something smaller? Using something like caching, Redis caching, for example, can make things more efficient. And then minimizing up, because that will minimize your IOPS and what's going backwards and forwards from the disk. Again, that's just designing for efficiency. Where you functions as a service is something that's quite interesting as well, because what functions as a service does is it allows you to just run your compute when you need it. Your essentially bringing a compute environment up when you want to run a piece of code, and then it goes back down when you're not using it. So anyone that's familiar with AWS and Lambda, for example, that's functions. That's an example of functions as a service. What you're paying for is just the compute that you execute. So if you're interested in actually pushing your costs down, that's quite efficient. But then obviously there's the considerations as to what's going on in the back end as well. If you now combine what I mentioned, where you take the modern language such as Rust and you put that into functions as a service, you now optimized for the language that you're using and the way the applications are actually coded, and you've also optimized for the compute environment that you're actually using. GPU as a service is another area which is becoming quite interesting. Where GPU, so many people would typically have run their own GPU clusters inside their data centers, and then they would just be running all the time. Now that's obviously, there's huge CapEx considerations as to why you would do that. If you're only using GPUs for very specific requests, so for example for inferencing requests on models, you can use GPU as a service and essentially just back that GPU request off to a provider. Where this obviously has some impacts on how you build your applications, because now instead of running a workload all the time on your GPUs, you're just sending them to GPUs as and when you need them. What this actually allows you to do, if you're running GPUs as a GPU as a service provider, you're incentivized to actually not run your GPUs all the time. You want to have them running only when there's a demand on them. You don't want them running when there's no demand on them, because you're just paying for GPU uptime that's not necessarily being used. So what you can start to do is actually start using the demand that's going into your GPUs and bringing them up and down as needed. What you do is you use the monitoring to understand the workload that's going into your GPU, and if there's no demand for the GPUs themselves, you can actually bring the GPU down. So you can use things like actually idling the GPU, frequency scaling, voltage scaling, and just deactivate the GPU. What this does mean is that you need to be very careful with your thresholds as to when you're building your applications or you're building your environment, your compute environment. You need to be able to understand where your thresholds are to when you bring these devices up and down. What you don't want to do is be in a scenario where you've not provisioned enough GPU capacity, all of a sudden there's a huge spike in demand and you aren't able to react to that quickly enough. So your thresholds have to be very carefully considered. What you're essentially doing when you do things like this is you're implementing a curtailment strategy, and the energy that you're saving when you do this is typically you would have two options. You would either have some type of agreement with your power provider, where you would actually have some type of sellback clause where you can actually release energy back to the grid. By being more efficient with the way that you run your environment, you can essentially run your data centers using less energy, and therefore you can release additional capacity back to the grid. The other option, and this is the slightly more CapEx intensive option, is you would use on-site batteries to store that energy. But then you've obviously got the cost associated with building those battery environments, of running them, maintaining them, and obviously they deteriorate over time as well. The efficiencies of these go down over time. So which is actually better? It really depends on how you want to consume it. It really depends on your own requirements. It really depends on how you want to consume energy and what the regulatory concerns are. What this goes to, though, is everything that I've spoken to up until now is about pushing your energy usage down as much as possible. But there is a floor that you can't go below, and that's the minimum load that is required to run your operations inside the data center. So if you now consider that there is that floor where you have a minimum amount of energy that you consume, what do you do with the products that you consume? And this is where this becomes quite interesting, because if you think of the data center, what the data center is actually doing, what I like to consider the data center as, it's a state change device. It's actually taking energy in one input and it's transforming it into a different output. And the way I look at this is the entire production line or the entire supply chain that goes into creating compute workloads contributes to this. So for example, here, I've only focused on electricity at the start. You've got your electricity supply chain, which your power generation transmission, that feeds into your data center. What is your data center producing as an output? It's producing compute capacity, which are then consumed by cloud computing services, enterprise applications, AI and ML workload. But what is your data center also producing? Heat. So if you now think of heat as an output product rather than a waste product, in the same way that your compute capacity that you're producing from your data center has downstream consumers, the heat that you produce in your data center also has downstream consumers. And this is where you come into things like heat recovery systems, as laid out on the diagrams that you see here today. And what this also goes to is, what does the future of AI data center design look like? So if you bring together some of the various concepts that I've spoken about today, you've got a resource manager inside your data center, which is looking at device orchestration, so bringing GPUs, CPU clusters up and down as needed, moving workloads around to consolidate things onto the minimum number of devices needed. You've got your battery systems inside your data center for fast access versus slow access, so your capacitors, high discharge capacitors, high speed capacitors versus your standard BESS systems, which is responding to your inference as a service requests going in. This is actually tapped into your energy grid, and you're actually saying, okay, well, what's the power going into the data center right now? Do we have the ability to release energy back to the data center via sellback? And then are we making sure we're producing all the compute that our consumers require? Are we producing the heat that our consumers require as well? And that's where these two boxes on the right-hand side, everyone is used to seeing the compute consumers as an output from a data center. What people aren't used to seeing is heat consumers as well. And this all comes back to something that Matt mentioned when he was talking earlier, is that heat isn't a waste, it's not waste. It's an output product that is produced by a data center. All you need to do is find the right consumer downstream, and if you can find that person, that isn't a waste product, that's a product. So if you now say that, okay, what is the optimum solution to DC design, where you actually co-locate with energy producers and heat consumers? If you consider the supply chain that I spoke about, where you've got energy generation, you've got compute consumers, and you've got heat consumers as well. If you bring all three of those into one location, you've got the optimum data center, because you don't have any quote-unquote waste. All of your energy generation, or as much of your energy generation that you want, is happening on site. Your workloads and your devices are being tuned depending on what's going on from a demand point of view inside your data center. Your compute is being consumed by your compute consumers, and your heat is being consumed by your heat consumers. So you bring all of these three concepts together, and you have what I consider to be the optimum design for a data center. So what is the end goal that we're trying to get to? It's about efficiency. It's all about making sure that we use the least amount of energy possible to generate the best products that we can produce. So make sure we produce the compute capacity we require, make sure the heat that we produce as an output is consumed, it's not wasted, it's actually consumed by that continuous supply chain that I spoke about. And what this eventually does is it prioritizes sustainability. You're now consuming all of these additional products, whereas if a leisure centre had to run its own heating infrastructure, for example, that's additional energy that's being used. By co-locating with a data center, they're taking the output from that data center, turning it as an input heat into their system, and therefore you're using less energy. So the important thing here is at the bottom of the sustainability box, consider state changed to be a product rather than a waste product, and that's the most important thing. With a data center, we take energy as an input, we turn it into compute capacity as an output, and we all think of that as a product. But the other product that's produced as part of that supply chain is heat, and we need to think of that as a product as well. And it's about marrying up that with a downstream consumer to make sure we end up with a very resilient, reliable, and scalable environment. And that's everything that I wanted to talk about. Thank you.